HowTCPWorks.com, the Transmission Control Protocol, part of HowTCPIPWorks.com. HowTCPWorks.com. In this section, we'll look at the transport layer of the OSI model. Then we'll look at the transport layer's key functions of segmentations and error detection and correction. Then we'll take a detailed look at the transmission control, or TCP, protocol and its mechanisms. We'll look at the TCP packet format and focus in on some key fields that are used for data transfer. We'll talk about the TCP connection sequence, what's called the three-way handshake. We'll also go through an example of how TCP transfers data. From there, we'll have discussion on TCP ports, and then finally talk about protocol connection types. The OSI transport layer. Transport layer protocols provide end-to-end communication and reliable data delivery. Now remember, when we talk about reliable data delivery from an OSI perspective, the transport layer isolates the upper layer protocols, the session, presentation, and application layer, from the details of data delivery. Generally, the session and above functions are part of an application, and when an application wants to transfer data, it will hand that data over to the transport layer. Then the transport layer will then provide the data delivery mechanisms with the help of the lower layer protocols to transfer the data. From the application's perspective, it really doesn't know what network layer is being used, what data link layer is being used. It doesn't know if it's using IP or IPX, Ethernet or token ring, and the application doesn't have to know because it hands the data to the transport layer, and then transport layer then manages it from that point of time. So there's this real isolation between the upper layer protocols and the lower layer protocols, and that's provided by the transport layer. Now, examples of the transport layer would be the TCP protocol in the Internet Suite of Protocols, also the UDP protocol that's part of the TCP/IP or the Internet Suite of Protocols. And the key things that transport layer components do is, number one, receives data from the application, and then it will segment it into the appropriate size pieces. And it may, and notice I said may, provide error detection and correction. Now you will note that we talked about error detection also on the OSI data link layer. The OSI data link layer is generally error detection only. The transport layer can do error detection and correction. Transmission Control Protocol, or TCP. Now, TCP is a single protocol, but as a single protocol, it is part of the TCP/IP or the Internet protocol family, or sometimes called the suite of protocols. It is a OSI transport layer protocol, and it provides connection-oriented data transfer. It's defined in RFC 793, and of course, it's part of the standard of TCP/IP suite of protocols used on the Internet. Transport layer segmentation. One of TCP's key jobs is to receive data from the application and segment it. Now, the maximum packet size, the maximum packet that can be sent out on the network, is really controlled by the data link layer. For instance, in the case of Ethernet, the maximum packet size is 1,518 bytes, including the Ethernet CRC. Now, the actual data transferred is much smaller because that maximum size of 1,518 bytes also includes the Ethernet headers, the IP headers, the TCP headers, and then what's left over is available for data transfer. Now, during initialization of the TCP/IP software, the data link layer and the transport layer will communicate, and the data link layer will inform the transport layer the maximum size packet. So then the transport layer knows that when it's going to send data, it has to divide or segment that data into pieces that the data link layer then can accommodate. Now, let's say in an example, the transport layer receives data from an application. It's a 5K byte file. Now, it knows that Ethernet can only hold in a packet less than 1.5K. So it will, the transport layer, subdivide or segment that data into multiple packets. TCP will hand the data to the network layer, which will in turn hand it to the data link layer for transfer. In our example, the 5K file will be divided into 4 different packets, TCP packets. TCP will hand each of those packets over to IP, which will in turn hand them into Ethernet, which will in turn send them on the network. The receiving station will receive those 4 packets, and then the TCP program in the receiving station will take those 4 packets and from those 4 packets recreate the original 5K file. Transport layer, error detection and correction. From the transport layer's perspective, there are two classifications of transport layer protocols. A transport layer protocol could be considered a connection-oriented service like TCP is, or a transport layer protocol could be considered a connectionless service like UDP. In a connection-oriented service like TCP, before any data is transferred, the TCP software in both machines exchange configuration information and create what's called a connection. Now, a connection is an agreement between the two machines to track all the packets that are sent between the two devices. The sending computer will expect to receive acknowledgement from the destination computer for all the packets that are sent. Now, if the sending computer doesn't receive an acknowledgement, it will resend the data until it is acknowledged or until it can determine that data delivery is not possible. And if data delivery is not possible, then this is where you would see a message like host not found, host not available. Now, in a connectionless service like UDP, there is really no error correction. There is error detection. It uses a checksum to see if the packet without corruption. But if a packet is delivered to UDP and it is corrupt, UDP will simply discard that packet and make no efforts to correct the error. So when we think about transport layer protocols and we think about the two types or two categories of transport layer protocols, connection-oriented versus connectionless, really think of connection-oriented services as having the capabilities to detect errors and try to correct them versus connectionless services, no attempt to correct errors. Transmission Control Protocol, or TCP mechanisms. In this section, we'll take a look at TCP mechanisms by first looking at key fields inside the TCP packet format. Now, we're not going to look at all the fields, but just the key fields that help us understand how TCP transfers data. We'll take a look at the TCP connection sequence, what's called the three-way handshake, how this connection is set up. Then we'll talk about connection-oriented data transfer, and we'll look at an example of how TCP transfers data. We'll then talk about how ports work, in particular TCP ports, and then from there we'll talk about protocol connection types. TCP packet format key fields. In our diagram here, we have a packet, and let's focus in on the data portion and the TCP portion. Now, the data portion would be another protocol and some data. For instance, this might be an HTTP packet inside the data, and inside the HTTP packet would be HTML. Now, HTML is the actual data that creates a web page. So the data has the TCP header information added to it by the TCP program. Then the TCP program hands the TCP header and data to the IP program. The IP program will add the IP header, including the IP addresses. It will then hand the entire thing down to Ethernet, in our example, which is the data link layer. The data link layer, Ethernet, will add its own header, including the destination MAC address and source address, and then the data link layer CRC. To that will become the Ethernet frame. That will be as you see it. Then remember, Ethernet will take the zeros and ones, that is the entire frame, the entire data, and then turn it into electrical waveforms with its physical layer encoding method. Now, let's go back to the TCP header. Now, I've listed out a couple key fields within the TCP header. The TCP source and destination port, the TCP sequence and acknowledgement numbers, and also the flags. These are not the only fields in the TCP packet, but these are some key fields that we're going to take a look at because they're important in data transfer. TCP connection sequence, the three-way handshake. When TCP is requested to send data, the first thing it does is it sets up a connection, and this must be done before any data is transferred. To set up a connection, the originating or source computer will send a connection request to the destination computer. That connection request is called a TCP data packet. This is step one, and includes its connection information. Now, its connection information may include the number of packets it will send, and then how it expects to receive acknowledgments. Now, keep in mind that this connection request packet is a TCP packet. So to really send it to another computer, TCP must hand that TCP connection packet to IP, who must then properly address it and add the IP headers, who must then, of course, give it to Ethernet, and then Ethernet would send it to the destination computer. In step 2 of the three-way handshake, the destination computer will receive the connection request from the originating computer and then decide to accept it or not accept it. Now, if it is not accepted, for instance, it may have all of its connections full already and not be able to accommodate any other ones, it will send back a negative acknowledgement or a NAC and essentially say to the originating computer, your connection request is refused. If the destination computer can accommodate another TCP connection, what it will do is send back an ACK packet. Now, in addition to the acknowledgement that, yes, I can do a connection, it will include its connection information. So that packet that returns in step 2 is not only an ACK, but also data and called a data ACK packet. Now, again, that's a TCP packet, and so the destination computer, the computer on our right in this case, would then have its TCP program and that TCP packet to IP. IP would then add its headers, include the addressing. It would then give it to Ethernet. Then Ethernet would deliver this second data ACK packet back to the originating computer. Now, once the source originating computer evaluates this data ACK packet, it will see that, yes, my connection has been requested, and then it will send back to the destination computer a final ACK saying, okay, we have a deal, we have a connection, let's start transferring data. Of course, in order for the source computer to send that step 3, that final ACK, it will have its TCP program give that TCP ACK packet to IP to Ethernet for delivery to the destination computer. Connection-oriented data transfer. The TCP sequence and acknowledgement number fields. TCP will receive data from the application to be transmitted. Now, in some cases, this data will need to be segmented into smaller packets. In any case, what TCP will do is it will assign an incrementing number to every byte of data that's going to be transferred. Then, when TCP is going to transfer the data, it will take the data, put it in the TCP packet, and then it will take the number of the last byte that's included in the data to be transferred and place it in the sequence field of the TCP header. When a packet is received by the receiving or destination computer, it will need to acknowledge that data. It will acknowledge that data by sending back a TCP acknowledgement packet, and it will take the sequence number that it just received in the TCP packet, identifying the last byte that was sent to it. It will take that sequence number and place it in the acknowledgement field of the ACK packet and then send that back to the sending computer. Now the sending computer knows that the receiving station has received that number of bytes. TCP data transfer. Now in this simple example, we have a sending machine on the left and a receiving machine on the right. Now our sending machine is going to send the first TCP packet. In that TCP packet will be 500 bytes of data. And when it sends the TCP packet, it will set the sequence field in the TCP header to 500. It sends that packet, and the first packet is received by the destination computer. Then it's going to send a second packet. Now this second packet also has 500 bytes of data. It's the next 500 bytes of data. So the sequence field is incremented to 1000, indicating it's the second packet. And when it sends that packet in this example, we're going to say it's not received. Now in the third step, the receiving station will say, gee, I've received one packet. That packet had the sequence field set to 500. I received 500 bytes. I will send a TCP acknowledgement to the sending station, an ACK, and I'm going to set the ACK field equal to the sequence field I received, which is 500 bytes, because I've just received one packet. Now, when the originating station receives that acknowledgement, it says, hey, wait, the sequence field's set to 500. The last packet I sent had the sequence field sent to 1000. Therefore, the receiving station didn't get the second packet. So what I'm going to do is I'm going to resend that second packet. So it'll create in step 4 that packet again, 500 bytes. It'll set the sequence field to 1000 because that's the packet that wasn't received, and it'll send it. In our example, the receiving station will receive that packet. Then it'll need to send an acknowledgement. Then in that acknowledgement, it will send the ACK field to 1000 because that is the sequence number of the highest byte it received. This is the second packet received, and it will send that acknowledgement back to the originating station. What are ports? Well, ports are a method for applications to identify themselves to TCP and the UDP programs. The reality is that on any given networking device that uses TCP/IP, there is only one TCP program. However, there may be numerous applications that use that TCP program. For instance, a server might have DNS running on it, it might have FTP running on it, it might be a web server, it might have a lot of different applications that are using the TCP program. So TCP has to have a way to keep track of the data that it's sending for these programs and also the data it's receiving these programs. So what TCP does, and likewise UDP, but which TCP does, is that it assigns a unique port number to each application. Now there are a possibility of over 65,000 ports, but port numbers are divided into server-side ports and client-side ports. Let's first talk about server-side ports. RFC 1700 reserves the first 1,000 or so port numbers for server-side applications, and it specifies that specific applications will have standard numbers. For instance, all web servers use port 80. All DNS servers use port 53. All mail servers that use SMTP use port 25. This is done because when a web browser wants to send a packet to a web server, it needs to put in the destination port. And by standard, the web browser knows that the destination port for the web server is always port 80. Likewise, the mail server, it's port 25, and the DNS resolver is always sending requests to port 53 where it knows the DNS server resides. Client-side ports are also used. Each client application, like a web browser or an FTP client, as it initializes, is assigned a port number. Now the client-side ports start above 1,000 because remember the first 1,000 port numbers are assigned to server applications. So as a client application initializes, it is on the fly or dynamically given a port number above about 1,000. Ports are used in this way. Each TCP packet that's sent out has a field called the source port and another field called the destination port. And when the TCP program sends that packet, it includes in the source port the port number of the application that created that packet. And in the destination port, it puts in the port number of the application that this packet is destined for. How ports work, an example. Now in our black diagram here, we have the picture of a server, and that server is running, of course, Ethernet, IP, and TCP. In addition, it has 3 different applications running that server. SMTP, which would be an email application. It has a web server application running and supporting the HTTP protocol, and then it also has a DNS server running. Now remember that each of these server-based applications has a specific port number assigned to it. In the case of SMTP, by standard, that server-side application would have the TCP port number 25. A web server always has the port number 80, and a DNS server has the port number of 53. Now in our example, we're going to see how 2 different packets are processed coming into the web server. On the left, we have an HTTP packet, and on the right, we have a DNS packet. Now, on our first example on the left, with an HTTP packet, that is a packet that is going to have been created by a web browser. Now, a web browser knows that when it creates a packet and gives it to TCP, that TCP will always put in the destination port number of 80 because an HTTP packet from a browser is always destined for a web server. A web server by standard always has the port number of 80. So the inbound packet has a destination TCP port of port 80. Now again, that packet will be sent to the server. The Ethernet program on the server will receive the Ethernet packet. It will look in, now this is, remember from our earlier sessions, we talked about the Ethernet type field. Ethernet will determine, based upon the type field, that the contents of the Ethernet packet is an IP packet. It will hand the contents or the data of the Ethernet packet to IP. IP will then do its processing, and including looking at the protocol ID field. Now remember, if the protocol ID field of an IP packet is set to the number 6, IP knows that the contents of its packet is a TCP packet. So in this case, it will forward the contents of the IP packet to the TCP program for continued processing. So now the TCP program will look at the port number. it'll see that in the packet that arrived from the left that the TCP port number is port 80. It knows that it should pass that packet, the contents of that packet, to the web server for continued processing. In our second example, the DNS packet on the right, when it's received, the TCP/IP destination port will be port 53 for the DNS server. The destination port number was set to 53 by the DNS client software that knows by specification that the server port number is always set to 53. Now again, this packet would travel up the stack. TCP would look at the port number and say, oh, in this case, it's a DNS packet. I need to forward this to the DNS program for continued processing. Do note that each of these packets, in addition to having a TCP destination port, has a TCP source port. Now remember, source ports are assigned by TCP/IP to client applications as they initialize, and there'll always be a number greater than 1000. In our example, we saw that the web server has received a request from a client. Now remember, that packet came in, it was processed by TCP. Now, in the TCP packet header, the destination port was set to 80 for the web server, and the source port was the source port that was assigned to the browser by the client when the browser initialized, and that was port 2048. So as the packet is received, the destination port is the web service port address, 80, and then the source port is the port of the application, the browser 2048. Now, when the web server wants to make a response, what it does is it flips the port, because when the web server sends the response, the source port is the port of the application that's sending a response. That's the web server 80, and then the destination port is where this packet is going to, and that would be the port number of the application that made the request. This is the client port number 2048. So on a response, the port numbers are flipped. So whatever port requested was the source on the request becomes the destination port on the response. Protocol connection types. One way to classify protocols, and this is the one we most normally talk about in network protocols, is that they can be connectionless or connection-oriented. A protocol that is connectionless will send out a packet and will really not verify if that packet's been delivered. In a connection-oriented protocol like TCP, what will happen is the protocol will set up a connection, track the packets, and then if packets are lost, it'll try to re-deliver them. Now, not only network layer protocols can be classified as connectionless or connection-oriented. We can, in a sense, classify all layers of the OSI model, or all types of protocols, it being connectionless or connection-oriented. Now, in the case of Ethernet, we know that it is connectionless, because if Ethernet sends out a packet and it's not delivered, Ethernet does not try to resend it. In the case of IP, IP is connectionless in that when an IP packet goes out and it's not delivered, does IP really try to redeliver? No, it doesn't. But who does try to redeliver? Who is providing reliable data delivery? In this case, it's TCP. Transmission Control Protocol, or TCP. Now, TCP is a single protocol, but as a single protocol, it is part of the TCP/IP, or the Internet protocol family, or sometimes called the suite of protocols. It is a OSI transport layer protocol, and it provides connection-oriented data transfer. It's defined in RFC 793, and of course, it's part of the standard of TCP/IP suite of protocols used on the Internet.